Okay, so we're going to look at a few more problems here, tests for convergence, but this time we have to decide which test to use. So this is 8 to the n over n factorial, and what I'm thinking when I see the factorial is ratio test. So the ratio test would ask me to basically take the limit as n approaches infinity of a sub n plus 1 divided by a sub n. And that is going to give me, multiplying by reciprocal, n factorial 8 to the n plus 1 divided by n plus 1 factorial times 8 to the n. And what we want to recognize about these things is n factorial over n plus 1 is just 1 over n plus 1 because we can divide out the n factorials, right? This is really n plus 1 times n factorial. And this is just multiplied by an additional 8. 8 to the n plus 1 is just 8 to the n times 8. So this should become the limit as n approaches infinity of 8 over n plus 1. And that limit is 0. Now, what the ratio test says is, if this is less than 1, which it most certainly is, then this series converges. And again, the idea behind it is that your consecutive terms are, their ratio is getting smaller and smaller and actually approaching 0. So each successive term is way smaller than the previous one, and that means that this series is going to converge. Now, I'm not going to do 56 because, oh my goodness, it just looks very similar to 54. And so I would suggest trying to apply the same test. Now, coming to 58. This looks like something I could integrate pretty easily, e to the negative x, and besides, it's a positive function that is decreasing, so the integral test applies. So let's consider the integral from 0 to infinity of e to the negative x dx. We actually know this converges. We can just claim it, because we know that the integral from 0 to infinity of e to the ax dx converges for negative a, and in this case, a would be negative 1. So we're actually done. We could find this integral definitely by taking a limit, but we already know it converges. So I'm just going to say converges by the integral test. Okay, 2 to the n factorial over n factorial squared. Oh my goodness, this looks like a ratio test. What do I think is going to happen here? Well, I thought originally that it was probably going to converge. Now I'm not really sure, but either way, I'm going to see what happens to the limit of consecutive terms as n gets large. This is going to become 2n plus 2 factorial when I distribute the 2 when I add 1 to the n, all over n plus 1 factorial squared, and I'm going to multiply by the reciprocal of a sub n, which is n factorial squared divided by 2n all factorial. All right, and let's see what happens to this limit. If it's less than 1, then it converges. If it's greater than 1, then the series diverges. And if it's equal to 1, well, we'll have to try something else. So this 2n plus 2 factorial and 2n factorial, everything divides except for the 2n plus 2 and the 2n plus 1, because after that would be 2n factorial up here, and those would divide. This is n factorial times n factorial. This is n plus 1 factorial times n plus 1 factorial. But n plus 1 factorial is simply n plus 1 times n factorial. And so we should be able to divide out the n factorials and simply be left with an n plus 1 times an n plus 1. Now you can spend some more time thinking about that if you need to, but this is what it simplifies to. And this limit, without going through all the steps, is going to be 4 because we end up with 4n squared over n squared. So interestingly enough, with 4 greater than 1, we know that this series diverges. So that 2 up there, that 2n factorial, is actually doing more damage than the n factorial squared. Interesting. It's a little bit surprising, but it's true. All right, let's look at 62 and 64. So 62, oh man, this is a nice rational function. N over n cubed looks like 1 over n squared. So I bet it behaves very similarly to 1 over n squared. I could either use direct comparison, but I prefer limit comparison. So I'm going to see if the limit as the ratio of these two, as n approaches infinity, rather, of the ratio of these two sequences approaches a constant, a positive constant. If it does, then they both have to converge. So I multiplied by reciprocal instead of dividing. And this will become the limit as n approaches infinity of n cubed plus n squared divided by n cubed plus 6, which is 1. So ratio test would tell us nothing with a limit of 1. But limit comparison test tells us, oh, 1 equals c is greater than 0. Then both sequences converge. Now remember, they both converge because we know this converges. That's a convergent p-series with p equal to 2. So if this had been 1 over n and we got 1 or 2 or whatever, then they would both diverge. So it doesn't matter what you get. This just tells us that they behave the same, and they behave in the way where they both converge because 1 over n squared is convergent. Now 64, when I see this negative 1 to the n minus 1, I think, man, that looks like an alternating series. This is really the sum from n equals 1 to infinity of negative 1 to the n minus 1 times 1 over the square root of 3n minus 1. So the alternating series test tells us if this piece of the sequence heads towards 0 and is decreasing, then this oscillating business will make the negative stuff eat up the positive stuff and will basically mean that it converges. So we need to show or claim with some certainty that the limit as n approaches infinity of 1 over the square root of 3n minus 1 equals 0. And that is certainly true. It's really 1 over infinity. Sorry, this is a little messy in here. And we need to believe that 0 is less than 1 over the square root of 3n. Now, if I plug in n plus 1 here, I get 3n plus 3. Minus 1 is 2. So 3n plus 2 needs to be less than 1 over the square root of 3n minus 1. Well, certainly. We added to the denominator. So this is less than this, and these are both positive. So basically, what that tells us is by the alternating series test, this series converges. So all you need to show with the alternating series is that the piece that's not alternating heads towards 0, and each successive term is less than the previous. So these are the two things we need, and they're pretty obviously true. And so the alternating series test tells us, boom, it converges. Okay, we're plugging away, 8 minutes in, 4 more problems, and then we can move on. So sine n over n squared. Oh my goodness. Sine n, this girl right here bounces up between negative 1 and 1. So I think that this is going to behave like 1 over n squared, and I'm going to try direct comparison. So what I'm going to do is I'm going to say, you know what? The absolute value of sine n over n squared is less than or equal to 1 over n squared. And it is greater than or equal to 0. Right? Direct comparison requires that the two sequences be positive, and now they are, and that's good. But I took the absolute value. But remember, taking the absolute value can only make this thing bigger. So that's fine, because if I can show this converges, this is bigger than that, and thus this would have to converge as well. So this tells us that the series of absolute value sine n divided by n squared converges by direct comparison with 1 over n squared, a convergent p-series. And thus, this also converges. Okay, and there's a little thing that tells us basically that if this converges, then this converges. Okay, this is really just bigger than this, and adding in some negative stuff will only make this sum smaller. So because the absolute value converges, then so does the original sequence. Hooray! Cosine n pi over n. Oh man, this is a tricky one. But the interesting thing is, if we plug in 1 here, if we think about the terms here, really what we're going to have is cosine pi over n, and then cosine 2 pi over n, not over n, cosine pi over 1, cosine 2 pi over 2, then cosine of 3 pi over 3. But cosine of pi is -1, and cosine of 2 pi is 1. So this is actually the same as -1 to the n minus 1 divided by n, because the pi, the 2 pi, the 3 pi, these are just making it basically alternate, because cosine is just jumping between 1 and -1. So basically all we need to show is that the limit as n approaches infinity of 1 over n equals 0, which it obviously does, and that 0 is less than 1 over n plus 1 is less than 1 over n, which is obviously true, and thus, by the alternating series test, this thing converges. So the interesting thing about having n pi is that when you plug in those different integers, this really just becomes 1 and -1, and it's an alternating series. Cool. Oh boy, 3 over ln of n squared. Ugh, man, I don't know about that. Honestly, I'm not sure. 3 over ln of n squared. I think this probably diverges because ln of stuff doesn't get that big that fast, but I'm trying to think how we might be able to show that. I don't know. Let's try limit comparison with like 1 over ln n. We know this diverges. Maybe limit comparison would work in L'Hopital's rule. I don't know. This may fail, but that's okay. The limit as n approaches infinity of 3 over the natural log of n squared times ln of n divided by 1, right? And that is going to be the limit as n approaches infinity of 3 natural log n divided by natural log of n squared. Interesting. I'm a little worried about this. This is going to give me, if I apply L'Hopital's rule, 3 over n divided by, this is going to be 1 over n squared times the derivative of n squared, which is 2n. Well, maybe I'm not worried about this. And this is the limit as n approaches infinity of 3 over n times, this is 2 over n, so times n over 2. Oh boy, this is interesting. So this is the limit as n approaches infinity of 3 halves. Oh my goodness. 3 halves equals c greater than 0. Boom. So that's interesting because the limit comparison just gave us a nice positive constant, which means both diverge. Got lucky there, right? Because we already knew that 1 over ln n diverged, so they both diverge. Huh, cool. All right, and finally, this is really n squared plus n divided by the square root of n cubed plus 2n squared. The numerator has degree n squared. The denominator has degree n to the 3 halves. Wait a second, that's really bad because the numerator has a degree higher than the denominator. So the limit as n approaches infinity of this sequence approaches infinity, and thus we're adding up infinitely many infinite terms. So this series definitely diverges in a really bad way. So don't get trapped into thinking, oh, I've got to do limit comparison or direct comparison or something. We should really always be checking to see whether the limit of our sequence approaches 0. And in this case, it does not.